Okay, let's get started. Today I'm going to talk about light scattering techniques, in particular relation to how we use them in structural biology. But the two main topics I'm going to discuss are static scattering, and that's using SECMALs, which you probably heard of. And this is a technique that we use a lot in the building. It's one of the most powerful techniques I think we've got in biophysics. And I'm going to finish with dynamic light scattering, which is one of the lesser used techniques, but still has some uses. So it's worth knowing about. Okay, so why do we use SECMALs? What is SECMALs? So the S is size-exclusion chromatography, so just normal running proteins for a column. The MALS part is multi-angle light scattering. If we use this, we can get a direct measurement of the mole mass in solution, and this has error rate of around 2 to 3%. So we can determine the size and shape of the molecule, which is called the radius of gyration. It's also a powerful technique because we can actually, as well as looking at proteins, we look at conjugated proteins, we can look at some components, we can see if things are glycosylated or if there's lipid binding, and we can determine how much the complex is made up of these components. We can also get precise protein concentration in this technique. And why would you use DLS? Well, DLS we use to measure the hydrodynamic rate as opposed to the rate of gyration. Again, it's done in solution. One of the main reasons we use it is often people want to measure lipid vesicles, want to know how big they are, but we also use it for quality control of proteins. So it's a good technique for optimizing buffers and things like that. Okay, so I'm going to do a few slides now just on light scattering, just to introduce the sort of physical properties of light. And then I'm going to go on to how we actually use these techniques. So there's lots of these people were obviously in the work in Cambridge, so we've got Lord Riley who discussed and made an explanation for why the sky is blue. He did it based on the observations from James Clerk Maxwell. So briefly, the reason the sky is blue is because blue and white light scatter more than the red and the longer wavelength light. So that's why we see it scatters. So that's caused from particles that are in the sky. So we observe this light scattering, and we base this on James Clerk Maxwell's equations and theories of magnetism. So basically, light has oscillating electric and orthogonal magnetic vectors, which you see here. Polarized light has a single electric and magnetic field oscillations. What's important is that the intensity of light is proportional to the square of the amplitude of the electric vector. So what Riley showed here then is that this electric vector induces oscillations of dipoles, and that means that they're polarizable. So we get the positive and negative dipole oscillation. What he observed was that with the oscillating dipoles, they absorb and re-emit light at the same frequency. Scattering is this elastic scattering or Rayleigh scattering, and that's what predominantly we use for the SECMAL. So there's another type of scattering we need to be aware of, and that was worked out by Gustav, and that's called scattering. So me solutions to Maxwell equations model this attenuation. Key things are using the radius of gyration and the wavelength of the scattering angle. Particles that are smaller than the wavelength, usually 10 times smaller than the wavelength, we get isotropic scattering, so the Rayleigh scattering. Once particles become close to the wavelength, we get this scattering, which is predominantly in the forward direction. So this becomes relevant. Most of the protein work is going to be smaller than 10 nanometers. We do stacking complexes that are bigger, and then scattering becomes more relevant. So me theory describes all scattering, but it is complex. The mathematics behind it are complex, but extreme. So large or small particles becomes simpler because of the dominant radius on the wavelength. And this is the bit where we're here. So most biological measurements are carried out here. So it's in this highly scattering regime. So what we want to do, or what people come to us to, is they've made a protein, they've made a complex. And they've seen it on the cryo-EM, and they might have some extra mass or something, I'm not sure of, so want to know exactly what the mass is that they've got in the complex. So the technique that we usually go to would be miles. So what we have is the amount of light scattered is proportional to the concentration. So light scattering is directly proportional to concentration. And also, all the mass is directly proportional to the light scattering as well. So we've got these two components. If we divide concentration, we're left with the mass. That gives a direct measurement of the mass. So larger particles scatter a lot more light. So it's important that we have good quality samples. So you need to have like a low void so it doesn't run in. So this is an extremely simplified version of what Riley described. So it's scattering like the larger macromolecular in solution. It's actually called the Riley-Gans-Debye theory. So this is the most important part. This is actually what he made. So it looks more complicated, but actually these are constants. This dNdc is the polarizability factor. These are numbers that we can look up. Then we have our mass concentration. This P is the angular term, so this is the mean scattering. So usually, if it's less than 10 nanometers, this is 1. And then the second virial coefficient, which I'm not really going to talk about. Usually at the concentrations we're using secmiles, and this value is much lower than 1, so it can be ignored. Okay, so what we want to determine from our via protein give us is we want to get this mass. So the way we do that, this dNd. So we have this differential refractive index. So proteins have universal dNd. So this is 62,000 proteins measured. The dNdc is quite a cluster around this 0.19. Usually the number you can measure it, but to say it always falls into this. And this comes because of the amides, the major contributor in the backbone. So the advantage of this is that we can measure protein concentrations from the refractive index range. It is useful because often protein, and if it are aromatics, it can be hard to measure. So we can do it independently. So the difference in refractive index between what's in the sample and what's in the solvent is directly proportional to the concentration in the sample. So we have this refractive index machine that can measure it, and that can then give us this C. So we have so we can measure the concentration precisely. So we've got these numbers, the dNdc, we measure the concentration for what these values are. So to determine the mass, we just need to work out these out. And this is where the multi-angle light scattering comes in. So this is the second machine. So this is the light scattering machine called the Dawn Helios, and these are all made by Wyatt. So this machine shines a 658 nanometer laser into the sample as it goes through, and we measure 18 angles. And so the light goes here, the sample's here, and then the sample scatters, and we have all these detectors around where we can measure this R theta. What we actually need is the angle at 0, but obviously you can't measure the 0 angle because this is incident light traveling all the way through. So what we do is we measure these 18 angles, and then we can plot them using this Zim formalism. There's different ways to plot these, but this is, for most applications, this is the correct version. Sometimes you have to use a different plot if it's very large. So what we've got here is simplify this. So we've got this 18 scattering angles, and we've got the scattered intensity. And we can plot that for a single point. And if we extrapolate this line back to 0, so we've got 0 concentration at the 0 angle, that gets a direct measurement of the molecular weight. So the intercept is the mass, and then this gradient, providing that we're over 10 nanometers, this gradient will actually give us a measure of the size of the particle, which can be useful, often is useful. So this gradient, so we call the gradient is the radius. What it actually is this radius of gyration. So if the angular dependence of the scattered light is measured, it's possible to determine the size of the molecule. So we measure the molecule size, and it's weighted by the mass distribution about its center. And you can plot this, so this RMS radius, or radius of gyration, can be plotted against the molar mass, and that can then give us the sample's conformation. So we can see if it's a random coiled, or if it's more sphere-like, or if it's forming like a coiled coil and more like a rod shape. So this radius of gyration is useful between 10 and 150 nanometers radius. So it's sort of limited in range, but it sort of falls into the range of a lot of complexes. Okay, so I'm just going to jump back a second and say, so this is what I want to show when we run it through the machine. So this is the RI detector signal that we get, and then this is the one of the 18 multi-angle light signal detectors. And what you see here is this is a mig per mil, 250 kilodaltons, mig per mil, but this is only 1.6 kilodaltons. So the refractive index gives us the same size peak, regardless of the size of the protein, because it is the mass. But when you see this, so this one is actually half a mig per mil for this larger one. But you can see, look at this signal, the scattering is much higher. So we get the bigger the signal, the bigger the molecule, we get a lot more scattering. That's important if you want to look at, or if you want to measure peptides and things like that. You have to put in a much greater concentration to get enough signal to measure. It's also useful sometimes to filter everything. We don't want anything in the buffers, because obviously anything in the buffers will create large spikes in here and mess up the measurement. And this is where the size exclusion part comes in, because obviously if we have, this is a 2.5 megadalton, but obviously the void, it can be even bigger. And then this void will scatter light, and it'll scatter a huge amount of light, and it can run into the signal. So it's really important not to just do a batch measurement, but to actually separate it. So I'm sure most of you have done size chromatography. You still sometimes see in papers people have actually, they do exclusion chromatography, and they run calibration curves. So they run known molecules and create a calibration curve, and then say this is the size of the molecule. It's quite a dangerous thing to do, because obviously it does run depending on the size, hydrogen volume, so the size of the molecule, but also it might interact with the matrix. It's dramatically affected by the buffer. So quite often you can see proteins won't run where you think they should run. They can elute either earlier or later. So it's important to just because you've run it on a size exclusion, don't think that you know the size. Okay, so this is how we have the instrument set up. So we have an auto sampler. So you can load up to 96 samples at once if you want. And then it goes through the size exclusion chromatography, goes directly into the UV detector, then into the light scattering, into the refractive index, and then it comes out either to waste, or if you want, we can also fractionate and collect the sample, and you can either reconcentrate it or use it for something different. So with one injection, depending on the column you use, it takes between 45 minutes to 60 minutes. If you use a smaller column, it takes 8 minutes per run, so you can get through the samples quite quickly. this is what a typical result looks like. So this is just BSA run through, which is what we always use as a standard and a control. So this BSA is a highly pure sample, but you can see in the green is the UV. You don't get any signal, but the light scatter you still see a little bit of signal because of how sensitive it is. Then the UV picks up the dimer, BSA, and then the molar is the predominant peak. These are the 18 different angles. The refractive index is also what we collect. So this is what we collect all this information in a single. This is how you see it presented in papers, where they'll show you show either the refractive index or the UV signal, whichever you are using to measure the concentration, because you can use either. It's possible to measure the concentration with the UV as long as you have the extinction coefficient of the protein and then the NDC. We usually use a refractive index. So at each of these points we collect every second. We collect a point, so every second we get 18 light scattering measurements. So then from each one of these you can determine. You can do your Debye plot, and each one of these is a Debye plot, and then you represent it by plotting it across the peak. So when it's nice and flat, we know that across this whole peak, this is around 66 kilodaltons. So it'll be 135 kilodaltons. And again, it's a nice flat line. So we know that it's a monodisperse, good quality protein. But sometimes the sample is not monodisperse. With this SACMALS, we can get the masses and can be averaged across the peak. So we can do this. MN is the number average, and W is the weight average. And we get both of these measurements. From that, we can then do this ratio. So if the NW to MN isn't 1, it means that we've got polydispersed sample, so different complexes or different proteins in there. If it's 1, it means it's a nice monodispersed sample, which is what we want. You can see this visually when you run the measurement. So because this is a machine that sometimes when you run it for, but also you train to use it quite easily. So if you're running it yourself and you see, go through the calculations, work through this, or the workflow, and you get a line that looks like this. And these light scatter and the refractive index are offset. You know that you've got a polydispersed sample. And this means either it's falling apart. So if it's a complex, it could be that it's breaking apart as it goes through the column. Its light scattering is offset because the larger molecules are scattering more light, so it looks like that. When it's monodispersed, they're perfectly overlaid. Okay, so SACMALS is something we do in solution. You can do it in any buffer. We try to sort of minimize something, so try not to have TSEP instead of DT. Try not to have too much glycerol, because that can start making it noisy, but in principle it works with any buffer. So it works for all proteins. We don't need to know the concentration because we measure that very accurately. It doesn't have to have UV absorbance. We can use samples that are not pure, but obviously the more pure they are, the better, but we do separate it anyway. Works fine with any label tags, these and things, because we're using this 658 laser. The mass we determine is completely independent of elution, and it's also independent of the shape and any interactions with the column. So if you've got a protein that's very stiff, or doesn't matter to this technique, and it's a pretty huge range that we can determine mass. So we can go from 500 Daltons up to 50 megadaltons, as long as we have the correct column. So here are some applications of what we do with it. So here we have, this is where we've got a very tight bind, and they wanted to know, the James Group wanted to know stoichiometry. So they got these 108 kilodaltons, and it went through the SACMALS, observed 317. So obviously this was a trimer. They wanted to know the ratio that it bound this antibody. So then we put, they put an excess of fat in, and then they got this measurement. So if it had a 1:3 ratio, it'd be 456 kilodaltons. We observed 455. So straight away, that they very quickly solved the problem. What is the geometries, and is it a monomer dimer trimer? I've said it's independent of elution time. Sometimes you can have complexes which are not as stable, so it's possible to cross-link them. So this was cross-linked prior to being run through. This was really an important experiment because the blue one says it's 780 kilodaltons. That helped the cryo-EM work because there was an extra bit of mass in the structure, and this showed that there was in fact an extra bit of mass in the structure. So there was actually 2 copies of the CN in this measurement. So then obviously you can go back to the cryo-EM and model that in straight up. Okay, something you have to be careful with when you do this technique is if you have a complex, or if it's a complex or something that forms a dimer or trimer, if it has a very fast on and off rate, because if it has a very fast on and off rate as it goes through the column, it will be diluted. But if it goes below the KD, you'll see that it falls apart. But because of fast on and off rate, it comes on and off very quickly. And in fact, instead of getting, if you had, say, a monomer dimer, you might get a monomer peak and a dimer peak. When it's got a fast on and off rate, it will give you a single peak. But if it's below KD, it will give you the wrong mass. That's something that can be deceptive. So you run the experiment, and that's when it's important that you sort of look carefully at the results. What you need to do then is you need to increase the concentration. And you can do that in 2 ways. If you can obviously concentrate the protein more, or in this case, we just used a much smaller column. So we used 5/150 column. So that increases the concentration. That made us able to shift these all to the expected size. It's quite obvious when you run it because, for instance, if you expect it to be 92 kilodaltons and you run it and it's coming out at 70 kilodaltons, well, there's kind of no way that can happen. It can't be 70 kilodaltons unless something's being cleaved. So a very quick test is to collect the fraction. If it's 70 kilodaltons, collect the fraction, rerun the fraction, and you probably look then like it's 40 kilodaltons. So you know that then the mass is changing with the concentration. So then you have to then increase the concentration. So you can get because of that, possible to get sort of a rough idea of the KD. So this is a sample again by Leo's group, where they thought this was going to be a dimer. So they predicted it was going to be a dimer. And at 15 mg per mil, it is a dimer, but you can see at 5 mg per mil, it's sort of intermediate. When you go to 0.5 and 0.25 mg per mil below, this is the monomer. So you can see these curves. So these are not flat, nice straight curves. And you can also tell by the shape of this that it has this long tail. So these are things to look out when you run your sample. If the peak is symmetrical, and particularly if you see this sort of unhappy smiley face going down, you've got the complex is falling apart, basically. Okay, so another thing we can do with this, so because we measure we've got 2 signals for measuring how much protein we've got, so the refractive index signal and also the UV signal. And we measure these at the same time. So it's useful because obviously we can have modified proteins. So if you've got proteins that are glycosylated or pegylated, or they're detergent, we can, as long as we know the DNC and the extinction coefficient, we can separate the peaks. So I'll show you an example. So this protein came out as 60 kilodaltons. So if you just run a normal analysis, you'll get this total mass and it's 60 kilodaltons. That doesn't make any sense because the protein was 46 kilodaltons, so it isn't a dimer. but they knew that it had glycosylation sites. It was expressed in the eukaryotic vector. So that's obviously it suspected that it would be glycosylated. So if we use the UV extinction of the protein and the literature DNDC, the UV for the carbohydrate, we can then separate this into the protein component and the modifier. So when we do that, we get 3 lines where you can see the protein component is now the correct size. So we know that that element, that extra mass was from the glycosylation. It's also possible to do this with detergent analysis. So again, we've got total mass came up here, much bigger than the size of the protein. This is actually a 5-protein heterocomplex with 0.1% digitonin in. So we put in the DNDC and extinction coefficients into the software, and we can separate this. And then we've got this 170 kilodalton protein, which showed that this complex had 1 subcomponent of each. Okay, so some quick practicalities surrounding this technique. So we always validate with DSA before we use it to make sure that everything's working properly. If you're using it, you need a litre of buffer and you need to filter it. You don't need to degas it. Don't use DTT if you don't have to. Keep glycerol to a minimum. The amount of sample we need, so we usually ask for 110 microliters at a mg per ml, and that's good for sort of any standard protein. If this is, we can run less, so you can run a lower concentration and you can run smaller volumes. But obviously, as soon it depends how good the protein is. So if the signal becomes too low, then the measurement becomes less accurate. So certainly a mg per ml is a good sort of starting range. If you use a smaller column, then you only need 40 microliters to inject, so you can minimize it. And like I said, we can collect fractions, so you can get the protein back. Okay, so I'm going to go on to DLS now. So this bit's quite a bit shorter than the last part. It's dynamic light scattering, and this actually feeds back into the signals that you'll see in a second. So I talked about this in the fluorescence correlation talk. So basically, larger molecules move slower with Brownian noise compared to smaller molecules. Diffusion causes scattering. So instead of measuring fluorescence, we're measuring scattered light with DLS. And it allows us to measure the size of the particles. So we can do that with basically this autocorrelation function, where this is a measure of test for self-similarity. I'm not going to really go through this because it was in the other talk. But what we get is this autocorrelation curve. So you put your sample into either a batch measurement or into a plate. You can use a plate reader, and you'll get this autocorrelation curve. Depending on the shape of this curve and the decay, we can work out using Stokes-Einstein equation, we can work out this dt. So this diffusion coefficient. So from the diffusion coefficient, we can see these are constants: temperature, 6 pi viscosity. We can work out this hydrodynamic radius. So the radius is it's important to think it's a sphere that would diffuse with the same translational coefficient. So obviously the proteins are often not spheres, but you will get a measure that is the hydrodynamic radius, not the exact radius. So DLS has a much bigger range. So you can see here this hydrodynamic radius works from 1 nanometer to beyond. This is where the static light measured. And you can see here that so BSA is here, the dimers here, thyroglobulin. So these, we couldn't really measure these with the static light scattering. We wouldn't get an accurate, reliable result. But with the DLS, you can measure these smaller proteins and say that's where most things are going to fall into that range. So in the biophysics, we've got different DLS machines. We've got this batch machine, cuvette-based method. If you use this, you have to be very careful. You have to clean it really well. Make sure there's no dust particles in your buffers or in the cuvettes. What we predominantly use is this Wyatt plate reader. this is really good because you can put 384 well plates, so you can put the 1,536 well plates in. We don't ever do that, but it doesn't. But you can. But it does take 384 well plates. The advantage of that is obviously you only need a smaller volume, so you can put 20 microliters into the well and then measure. And also, you can do, this machine will do thermal gradients, and you can run lots of different wells with lots of different buffer concentrate, lots of different buffers, and do large screens. So that's really what it gets used for, is large screens of buffers and physical work. So this is the plate reader version. So you can do a rapid check on the sample quality. So it's because larger molecules scatter a lot more light. It's really obvious if you've got aggregation or if you've got a problem, you see that immediately. So it's a fast assessment of protein aggregation. Use it to determine the size of extruded vesicles in this buffer screening. So this is what a typical DLS data would look like. So when we measure this, we get, so it's important to see this because when you analyze it, it's possible to do this number analysis, the volume analysis, or intensity analysis. So the intensity of scattering is proportional to d to the power of 6. This is from the Rayleigh approximation. So something that's much bigger will scatter. So this is, say we've got 5 nanometers and 50 nanometers. The 50 nanometers will scatter 1,000,000 times more light than 5 nanometers. So even though we've got two populations where they've got the number of the spheres are exactly the same, this is what we measure. And this is the true measurement. So the intensity is the true measurement of what we're getting. Volume and number are mathematical fits to the data. So it's important that it's possible that you can jump to this one and we know this is correct because we made this up and we know it's 1-to-1. But if you've got an unknown sample, it's really important to look at the intensity first. And it's absolutely fine to use these ones, but you do look at the intensity because obviously something that's going to really skew the results. So things to remember if you want to use this technique. So in general, you need about 0.2 mg per mil for a standard protein, and that's 20 microliters, not 20 mils. So 20 microliters, 0.2 mg per mil. That's for something, say, like BSA lysozyme. If you've got bigger protein, then you can actually get away with much less. The dynamic range of this machine is really high, so it can adjust the laser and it can adjust the gain. It does that automatically, so it's very simple to use. The things you have to, obviously, if you want to use this, we can train you to use it. But the thing that's important to know is that we get this scattering intensity and we get a count rate. And this count rate shouldn't go above 500 kilocounts per second. So quite often you'll put your protein sample in, you start the recording, and you can see straight away what the counts are. If it's above 500 kilocounts per second, then you're not going to get accurate results because there's just too much concentration in there. So what's usually good to do is just do a quick dilution. So when have your protein, and just do a 2-to-1 dilution down. And then what you'll see, if we get this 500 kilocounts per second, if you dilute it, basically the count should be reduced by 2. If that isn't the case, then you've got too much protein. And then it will give you a result, but it won't be accurate. And we also get this polydispersity value. So on this machine, you have like under 20% is considered good. So if it's less than 20%, it's monodisperse. Okay, so just to finish up, so what we actually have as well on our SEC-Miles machine is, so instead of having the 18 angles that we have around in here, one of them was removed, and we actually there's a DLS detector in there as well. So if we run SEC-Miles, we get, as well as getting the RG, the radius of gyration, we can also measure the hydrodynamic radius. So we can do this in one. Each of these points, you see, we'll get this autocorrelation curve, and then we can say get the radius of gyration. So that can be really useful because if we compare Rg to Rh, this comparison can tell you about the structure. So for instance, for something that's globular, so like a severe, if you do the Rg divided by Rh, it should be around 0.77. And yeah, this pretty much holds true for most small proteins. So here we go. This is the radius of gyration. This is lysozyme. Its true size is around 3.5 nanometers. The measured radius of hydration is 2.2 nanometers, and the radius of gyration is 1.8. So that gives this 0.77. So this is globular. This is an example that this was done in Matt van Bruegel's lab. And this is where they wanted to know the shape factor. So they knew the mass, so they're using the SEC-miles, they got the mass of 74 kilodaltons, it's calculated to be 76. The radius of gyration is 8.7 nanometers. So it is below the 10 nanometers, but it's not a strict cutoff for 10 nanometers. So it is possible to measure these. But what was important is obviously the rate of hydration was very different. So Rg divided by Rh then gave this 1.6. So that's consistent with a rod-like shape. So they knew then that they had this coiled shape and it wasn't running like a globular. And say this is all information that every time you do a run with the protein, you get all this. So quite often you don't use it. You might just want the mass, but it's just important to know that that information is in the data. And we can help you get that out. Okay, the last thing to finish up is just a couple of other ways we use light scattering. So this is something that Jan's group have used in the past. So they use it as a kinetic signal of mass change. So basically when they have their, we show here, they have these filament polymerizations. So as the filaments grow bigger and bigger, they scatter more and more light. So by simply measuring scattering at 90 degrees using a basic fluorimeter, you can get a good kinetic measurement of filament assembly. So sometimes if you're working with proteins that do form filaments, scattering can be a useful technique to use. And obviously don't forget, we talked about in the top 5 is this mass photometry. And again, that's based on scattering and interference. Okay, so to finish up, what we got, we can measure mass in solution. So it's extremely accurate. We don't need any prior information, just need a reasonably pure sample. And that's say within a 1 to 3%, we can measure this. It's got a very large range and it's shape and conformation independent. We can work out the radius of gyration and the hydrodynamic radius from the SEC-miles, or you can use DLS to do the RH on its own. They're all solution based, so they can all run in whatever buffer your protein prefers or what it's happy in. It's quick and automated. And yeah, so for the DLS, you can use very small amount of protein. And for the SEC-miles, it is a bit heavier on protein, but you can get it back from fraction collections. And it's an extremely useful number. It's one that you'll see in a lot of papers. It's in a lot of supplementary figures because it's an exact measure of mass. Okay, and if you want any advice or to discuss, or you want training in either of these techniques, then just email Stephen or email me and we can get you started on it. Or if you've just got, sometimes you just have the odd sample and you can just arrange and we can run that for you. So whichever you want to do. So thanks for coming.